Welcome to The Explainer. Today we're diving into the future of water, moving from sinking cities all the way to AI-designed skies. For literally millennia, humanity's go-to instinct has been to just dig down into the earth whenever we need water. But as we're going to see, we are hitting a terrifying tipping point.
So ask yourself this. What actually happens when our primary water source is literally pulling the ground right out from under us? It's wild, but the reality of land subsidence is incredibly jarring. Basically, when we pump out groundwater faster than the Earth can naturally refill it, the land physically sinks. Look at Jakarta. Recent research shows parts of that city are dropping by a massive 20 to 28 centimeters every single year. And it's not just the roads and buildings getting wrecked. All this groundwater depletion triggers saltwater intrusion, which completely wipes out vital coastal mangrove ecosystems, like the ones in Pantai Indah Kapuk. We're essentially destroying our natural defenses against coastal erosion, all just to get a drink of water.
And hey, this crisis isn't just about the sheer volume of water we're taking, it is heavily about the quality. This leads us to a colossal public health toll. We're talking about 843.6 million people globally who are now dealing with renal or kidney dysfunction. To put that into perspective, that's almost 1 in 10 people on Earth. Studies popping up from Sri Lanka to Taiwan to China are showing a direct correlation between prolonged exposure to contaminated drinking water and the biomarkers for this terrible renal disease. Now, historically, groundwater was basically the gold standard for safe water, right? It was pristine, naturally filtered, literally the lifeblood of terrestrial food chains that kept springs and wetlands thriving. But fast forward to today, and a lot of it has devolved into a literal ecotoxicological nightmare. It's increasingly laced with nasty heavy metals like cadmium and arsenic, mostly thanks to industrial discharge. Get this, in places like North Jakarta, up to 80% of groundwater samples completely fail health standards. And the worst part? These toxic metals dissolve super easily, they stick around, and they bioaccumulate. That means they build up across multiple species, completely messing up metabolic processes from tiny organisms at the bottom of the food chain all the way up to us.
Okay, so the bottom line here is absolutely crucial. We need a massive ecological reset. And that brings us to our first real ray of hope, the natural antidote, atmospheric water. Instead of pumping toxic water from deep underground, we need to start looking up and harvesting it right out of the air. Specifically, natural dew harvesting is stepping into the spotlight as the purest, most natural alternative to these exhausted, polluted aquifers.
Let's break down exactly why dew water is such a game changer. Think of natural dew as nature hitting the reset button. First off, it usually has this beautifully neutral pH, sitting right between 6.5 and 8.5. It's packed with dissolved oxygen, around 9 milligrams per liter, and it has virtually zero heavy metals, none of the bad stuff. And maybe the biggest win? It dramatically cuts down our reliance on those vulnerable underground aquifers. We're seeing research from Morocco to India proving how much dew contributes to keeping soil moist and restoring whole ecosystems. Plus, when it's processed correctly, this stuff perfectly meets the strict 2024 WHO drinking water guidelines. It's 100% safe for us, and it gives the Earth a chance to finally heal. But, of course, there is a pretty massive geographic catch. When you look at the global map of desert and arid ecosystems, and we're talking about areas spanning over 100 countries here, the air is just so incredibly dry that your basic traditional dew collection completely falls apart. It just won't work. Yet these are the exact same regions where water stress is off the charts, and clean drinking water is desperately needed for farming, power, and, basic human survival. So the big question is, how on earth do we harvest atmospheric water when there is barely a drop of moisture in the air?
Well, the answer to that actually lies in atomic engineering. Enter metal organic frameworks, or MOFs for short. The best way to think of MOFs is like highly programmable, microscopic water sponges made out of crystals. They are specifically engineered to grab water vapor right out of the air, even when you're in incredibly dry, ultra-low humidity conditions. And then, they just release that water using a tiny bump in temperature, like normal ambient sunlight. They literally trap water molecules inside these highly ordered, hydrogen-bonded networks within their crystal structure. It is, without a doubt, the high-tech evolution of atmospheric harvesting.
Over the last decade or so, chemists have basically grown an entire evolution tree of these moths, custom tailoring them for water harvesting. They've engineered these incredible materials to create what's called an S-shaped isotherm. Now, in plain English, that just means the moth suddenly acts like a superpowered vacuum for water at very specific low humidity levels.
By mixing and matching different chemical links and tweaking the space inside the pores, researchers can literally wring water out of the driest desert air and do it without wasting a ton of extra energy to squeeze the sponge out.
Now let's talk about supercharging that discovery process with AI. See, designing these intensely complex, atomic-level structures using old-school trial and error, that takes years. Trying to find the exact right balance between stability and how much water it can hold is literally like finding a needle in a microscopic haystack. But look at how AI completely flips the script. By bringing in machine learning and large language models, scientists are skipping decades of chemical guesswork. We've got AI agents interacting directly with the structural data of moths. They can predict the synthesis, the structure, and the properties before a human even steps foot in the lab to make it. The AI pinpoints the exact microscopic environment needed to trap a water molecule in as little as 15% humidity. It's predicting outcomes in minutes that would take human chemists years to stumble upon.
We are frankly making an absolute leap in materials science right now. Think about it. In the past, human-guided design meant finding the perfect muff through a painfully slow, iterative process. It relied so much on a chemist's personal intuition, which naturally limited how far we could optimize things. But switch over to AI-assisted design, and suddenly we jump to highly accelerated data mining. AI uses predictive synthesis and inverse design to meticulously fine-tune the crystallinity and max out that water uptake capacity. It is essentially reverse engineering the exact atomic sponge we need based purely on cold, hard data. It's amazing.
Okay, so we've engineered this perfect, miraculous powder in a high-tech lab. Great. But we're moving from atomic sponges to real-world harvesters now. Because how does a pile of microscopic powder actually help a family living in a bone-dry desert? We've got to scale this up.
The process of turning that engineered powder into a functional, completely off-the-grid device is just incredibly elegant. It all runs on a simple 4-step cycle. Step 1 is absorption. The MOF material just sits exposed to the ambient desert air, pulling in and concentrating that invisible water vapor. Step 2 is enclosure. The harvester gets sealed off from the outside air. Step 3 is condensation. Regular old solar heat from the sun warms up the MOF, which forces it to release all that trapped vapor into a liquid state. And finally, Step 4, collection. Pure, perfectly drinkable water drips right down into a container.
And I really want to emphasize something here. This is not just science fiction. Out in the actual field, we have active multicyclic models running on solar panels alongside passive models that literally just sit out in the sun doing their thing. And they are already operating autonomously in some of the harshest, driest environments on planet Earth, like Death Valley and the Mojave Desert. They are out there right now, actively pulling clean drinking water out of bone-dry air, proving beyond a shadow of a doubt that this technology is ready for the real world.
So, I'll leave you with this. What if every single home, no matter how unforgiving or dry the climate, could pull its clean water directly from the sky? Just imagine the incredible ripple effect that would have on global human health, on resting our shrinking aquifers, and on saving our sinking cities. We are looking at a very real future where water security is completely decentralized and accessible to everyone. And it's all driven by this brilliant synergy between natural atmospheric moisture, advanced reticular chemistry, and artificial intelligence. Thank you so much for joining me for this explainer. I hope it helped you grasp the truly fascinating future of our water supply. Keep looking up, and I'll catch you next time.